So, the next one is to see how these now translates themselves to the presence of the newer space groups. The next space group we discuss will be P21 upon m. So, what is the take home lesson in 2 1 upon m? In the case of 2 1 upon m, the mirror symmetry is the one which shift by 1/4. So, you see in this diagram the mirror symmetry. If you look at only the symmetry diagram, the symmetry elements diagram, we draw this unit cell and draw the centers of symmetry at the origin. Then we know that the two-fold 2-1 screw axis will coincide with this. So, we write the 2-1 screw axis to coincide with the direction of the origin along the B direction, because the unique axis is B, and we have shown the AB projection as before, as always. So, we see that because of the presence of the 2-1 screw and the center of symmetry at this position, the same will repeat at half position, and then of course, the full unit cell. In addition, the centers of symmetry will develop at the half positions along the B direction. Notice that since there is only one axis of rotation in a monoclinic system, we should remember that the symmetry operations are restricted to around the y axis, which is the unique axis. So, we do not have any other symmetry elements which will come in a monoclinic system. So, there is only one unique axis about which the symmetry operation take place. So, in other words, if it is a two-fold axis operation or a mirror alone or a combination of 2 and m, whether it is a 2-1 by C operation, all these symmetry operations are restricted to operate only along the y direction, and that is why it is called a unique axis in a monoclinic system, and that B axis therefore is the one which shows the presence of the two-fold along with it. Just as we saw in the previous slide that the mirror now comes 1/4 removed from the origin. Since there is a mirror that is generated here, another mirror will generate at 3/4. So, the equivalent point diagram now. So, this is the symmetry diagram. In the symmetry diagram, therefore, we have the center of symmetry indicated at all the corners of the unit cell as well as at the half positions along A and B. The presence of the 2-1 axis is illustrated along the B direction and also at the cell edges, and also halfway distance along the A direction. And the mirror symmetry is now moved away from the origin, the intersection of the origin and the 2-1 screw axis by 1/4. So, the mirror now appears at 1/4 and 3/4, and therefore, the symmetry operations now become slightly different. So, if you take the point number 1, operate now the presence of the 2-1 screw axis. The 2-1 screw axis will take this, rotate by 180 degrees, translated by this unit. The rotation of 180 degrees is as usual x bar and z bar, and the addition of half unit is y plus half. So, you get to this point number 2. 1 unit translation of the point 2 will bring it inside the unit cell. So, we have generated 1 and 2 inside the unit cell. Now, the next operation is the mirror operation. The mirror operation is not now associated with the y equals 0, but we have to move it by 1/4. So, the mirror operation is moved by 1/4 along the B axis, and because of the fact that mirror is 1/4 removed, you will add, for example, 1 now goes to the point 3, which is now x y z, going to x instead of x y bar z, it adds on a half unit with that one, and therefore, we get x y bar plus half z as the third equivalent point. Why do we get this half? We get this half because the mirror has moved by 1/4, and there is a mirror at 3/4 as well, which is going to generate the further operations in the other unit cells. So, you see now that we have point number 1, point number 3, and this point which was translated, all 3 in the unit cell. So, there must be one more. That one more is automatically the center of symmetry operation, because if you now take point 1, operate the center of symmetry, you go to point 4. 4 now can be translated by 1 unit in the A direction and 1 unit in the B direction. You will get to this point. You notice now that the unit cell is up here, and you have 1, 2, 3 and 4. So, there are 4 equivalent points again in P2 by m, just like P2 by m, which you saw just now. P2 by m has all the 4 around the center here, and because of the presence of 1 axis and the mirror now moving to 1/4 position, you will get the different space group identification with respect to equivalent points. Now, the equivalent points are the ones given below. Notice that you operate again x bar, y bar, z bar, you operate the center of symmetry again, you will go here, operate the mirror symmetry, you will go there, and operate the two-fold, you will 2-1 screw axis, you will go there. So, the symmetry is still maintained, and therefore, the property of the group is still maintained. That is the requirement. So, P21 by M therefore, is a space group where we have moved the mirror by 1/4, and the movement of the mirror by 1/4 is the one which kind of indicates the presence of the translation involved symmetry element. This only happens in crystal systems, because we are now it is required that we have a unit cell and therefore a lattice in our, and the object should be confined within the crystal in order to have this symmetry. He said start, so I started. So, the space group is P2 by M, and the equivalent points clearly indicate now the presence of the mirror symmetry, which is removed by 1/4. So, this operation, which is operation number 3, symmetry operation number 3, has a half translation associated with y bar. That is the one which invokes the presence of the mirror symmetry. So, these are the 4 equivalent points in case of P2 by M. We will now shift our attention to the space group P2 upon C. Now, the moment we see the space group as P2 upon C, we know the lattice is primitive. The presence of 2 upon C, in fact, the full symbol for this space group should be given as the symmetry along the A direction, or the symmetry along the x axis, symmetry along the y axis, and symmetry along the z axis. So, it should read P1 2 by C 1, but it is normally the 1 symmetry is not indicated. So, when we say P2 by C, it tells us 2 things. One is that whatever symmetry operations we are having, the 2 by M point group symmetry, is along one single axis, and this presence of the two-fold indicates that it is monoclinic symmetry. Monoclinic symmetry is the one which will have the two-fold symmetry alone along the y axis, along a given one axis, and that we take as the y axis. So, the symmetry operation 2 divided by C, 2 by C, indicates that we are dealing with a monoclinic system. So, if someone gives you the space group, in principle you should be able to automatically find the crystal system. You not only find the crystal system, of course, the moment you see the lattice identification, you see the lattice also, the Bravais lattice that is associated with it. The examination of the symmetry that is given here, convert it to a point group symmetry. Suppose you are given 2 by C, the corresponding point group will be no translation involved, that is 2 by M. So, it is a centrosymmetric space group, and we conclude that it is a 2 by M point group. We have the primitive lattice, and therefore, this is a monoclinic system. So, we say now uniquely by looking at P2 by C, we identify it is a monoclinic system, it is a primitive lattice, and then we now can also say the operation of 2 by C, just like 2 by M operation, will give rise to 4 equivalent points. So, by just looking at this, we can anticipate how many equivalent points come. This is in general, and in the unit cell, and also we tell us about the way in which this operation takes place. We have already seen that whenever there is a non-translational component that is associated with the symmetry operation, that particular symmetry which is not involving the translation symmetry, that is the two-fold, will have to move by 1/4 from the origin in order to accommodate the requirement of 2 by M symmetry, which is the presence of the center of symmetry. Just to repeat, this presence of the center of symmetry will necessitate the symmetry which is not having a translation component to be associated with a distance movement of 1/4 along the direction perpendicular to the axis, to the unique axis. And therefore, you see that if you look at this two-fold symmetry, the 1/4 symmetry is indicated very clearly here. That means, the two-fold is not with the origin 0 0 0, but the two-fold symmetry is 1/4 removed. Let us say it is coming up by 1/4. So the two-fold axis will pass somewhere there at 1/4 if this is the C direction, and of course it can come at an angle beta. So the symmetry operation therefore now will be these are the equivalent points which are given. You see that the equivalent points are very similar to P2 by m. If you go back and see the P2 by m, the symmetry points are all clustered around this origin. Once again they cluster around the origin, except that the point 2 and point 3 you notice here, we will see the two-fold axis 1/4 from here, and as a consequence they move by half unit. So these two positions therefore have a half translation in a direction which is perpendicular to this plane of operation, and therefore it is not really perpendicular, it is along the C axis. So we have to remember that in a monoclinic system the third axis is not at 90 degrees, right. So this is now therefore going along the C axis, it is half translation along the C axis. Please remember the half translation along the C axis will not involve a 90 degree angle, which is very important in monoclinic systems. So it is moved by half the translation. So what is important is the unit cell dimension. So whenever there is a glide operation or a 2-1 screw operation, what is important is the dimension of that particular axis, not the orientation of that axis about which the operation takes place. Okay. So we therefore have the mirror operation which is 1/4 removed, and then we have the symmetry which is generating the C glide system, and the equivalent points are given below. So you see here that the 1 to 2 operation involves the two-fold operation, but the two-fold operation is now at 1/4 the distance along the C direction. So it becomes z bar plus half. So it is x bar y z bar plus half. X bar z bar will tell us that it is a two-fold rotation. The presence of half will tell us that the two-fold axis is located 1/4 along the C direction. Now if you look at this point x y z and see how point 3 gets generated, the point 3 is now a mirror symmetry operation, and it is not just a mirror symmetry, we see that there is a translation of half involved in this, and so you see x y bar half plus z, the C glide translation symmetry is added on here, and so you get this presence of the C glide. If you just look at these two, it represents straight away the C glide symmetry elements. And then of course because of the fact that it is a 2 by m point group symmetry, P2 by C will also have x y z and x bar y bar z bar, the center of symmetry. So a full description of the P2 by C is given here, but what is normally required is that we have to give this symmetry information separately, the symmetry operation information separately, equivalent point positions separately, and that is how it will appear when we examine the international table very soon. The international tables for crystallography is the handbook that is required to identify all the symmetry elements that we can generate in a space group, taking into account the requirement of translational periodicity requirements of moving the axis or the mirror planes by 1/4 the distance in this particular set of examples. As we go to higher systems where we have 3-fold symmetry, we have 4-fold symmetry, we have 6-fold symmetry, the amount of translations can be lower than that. In other words, it is not exactly half, it could be lower than that. In fact, we will see one such case in a monoclinic system very soon, and that will tell us that the movement of the axis need not always be half, it can be even 1/4, and that is the symmetry which you will see in the case of C2 by C. We will go there in a few minutes from now. So what we see here is therefore the case of the involvement of the translation involved components and the way in which the symmetry operations occur by shifting the non-translation involved component in these cases by 1/4 as we have seen here. Now we come to the case of P21 upon C. P21 upon C is by far the most important space group from the point of view of particularly small organic molecules. Most of the small organic molecules which do not have a asymmetric carbon, they tend to go into P21 upon C, because P21 upon C appears to be the most comfortable space group to lie down in that sense. Suppose you are given a choice of this chair on which I am sitting and a stool on the across the lecture hall, and then a sofa across at the back of the hall, you obviously prefer the sofa. So the organic molecules, they want to relax. Keeping their flexibility intact, they want to relax, and when they want to relax, the flexibility is still allowed with the relaxation. So when you are sitting in a sofa or when you are sitting on this chair, it does not matter, you will still be moving around, right? But the movement around this sofa is much more comfortable than the movement in this chair, because you are restricted here. In a sofa you can spread your wings. So effectively organic molecules spread their wings with the flexibility that is allowed to them, and that is why P21 upon C is the most favorite space group for most of the organic molecules, particularly when there is no asymmetric carbon in them. It is not necessary that organic molecules must crystallize in P21 upon C, but that is a preferred space group. Any other crystallization effort can take it away from P21 upon C, will give rise to systems which will have higher energy located with them. So it could be disorder. For example, if you take it to a higher system like a tetragonal or a cubic system, the organic molecule tends to be disordered, and that is an issue we will discuss when we actually look at these details of structures and how intra and intermolecular interactions are important to study. At that time we will look at the energetics that are involved. So P21 upon C therefore is a space group we will study in enormous detail. So what are the operations here? The operations here are a 2-1 screw and the C glide simultaneously at an intersection point. So you quickly realize that 2-1 and C will have to move from each other. They cannot be associated and intersect with each other, because the point group symmetry happens to be 2 by m. Because the point group symmetry is 2 by m, you need to have a center of symmetry, and the presence of the center of symmetry and the requirements of the definition of a group will invoke for every given xyz across the center of symmetry located 0 0 0, you will have to have x bar, y bar, z bar. So one of the advantages is that in this case we already have the two equivalent points already identified in P21 upon C. One of the questions which I would like to pose to you, of course I have already shown it here, there are only 4 equivalent points even in the case of P21 upon C, and these 4 equivalent points can be derived based upon the diagram which is given here. One could have spent some time on checking out what happens if 2-1 and C intersection point can be taken as an origin. This could be probably an assignment in your coursework which will be given by one of our TAs. What will be the equivalent points if 2-1 and C intersect at the origin? Generate the equivalent points and see for yourself and convince for yourself that the presence of center of symmetry gets invoked, just like what we have seen in these two examples, and see that the presence of the center of symmetry is not then at the origin but somewhere else. In fact, that somewhere else is very interesting. I want you to work it out and find out where is that somewhere else, and that will be very interesting to find out. That somewhere else will be not at half, it will be at 1/4. And this is something which I thought I will derive, but I was thinking that we can as well derive it when we take a little more complex space group like P21 2-1 2-1, where there are two two-fold axes, two 2-1 screw axes. Do they really intersect with each other? That would be a more exciting discussion than the discussion with P21 by C. But with P21 by C, I thought a good assignment would be to see what happens when the 2-1 and C are coincident with the origin. So that could be given as a home assignment or a assignment in the course to carry the marks as well. This is something very important, so it can carry the marks as well. So now let us examine the situation where we have taken care of this with the fact that the definition of 2-1 by n and 2 by C convinced us that whenever we have the center of symmetry, the center of symmetry should go to the origin. So we decided to put this at the origin. So if we put this at the origin, then we have the point number 1 now goes to point number 2, which is the 2-1 screw operation. Now the 2-1 screw operation is coincident here with respect to the presence of the two-fold 2-1 screw, but you see that it is now removed by 1/4. Notice that in this particular case also it was removed by 1/4, and we argued that it is due to the presence of translation associated with C glide. Here also we have a C glide, and therefore we move the 2-1 screw axis 1/4 away from the origin. So when we move this 1/4 away from the origin, then you see that 2-1 screw axis will develop at 1/2 this position, again 1/4 removed, and so on. So the symmetry operation 1 therefore will take this position 1 to a mirror position and then half translation. So this half translation will generate this point 2, which is half minus. Okay, that means it is below. So what would be the equivalent point? If there was only a 2-1 screw axis, the equivalent points would have been x bar, half plus y, z bar. Now along the C direction we have to move by 1, the axis moves by 1/4, and therefore the position of the equivalent point moves by half, because the next operation on this particular symmetry element should take it to the next unit cell and it should overlap with 1. That is the requirement of a definition of a group, and therefore we see that the equivalent point now is x bar, z bar. Z bar also gets a half added to it along with the y plus half. So it is fairly straightforward to understand P21 upon C. The presence of 2-1 as well as C will move both the axis by 1/4. 1/4 along the direction which is perpendicular to the AB plane in case of the 2-1 screw axis, and in plane with respect to the C glide. So the C glide now, as you have marked here, will move by 1/4. So C glide moved by 1/4, the 2-1 screw moved by 1/4. So what happens if you move the C glide by 1/4? So the point 1 now has to generate point 3. The point 1 generating the point 3 now will have a mirror half translation. So it should have been, if that was to be at origin, it would have been what? It would have been x half plus y bar and z. Now you notice that you have moved it by 1/4 along this direction, and therefore you have to add another 1/4 to the z value. So you have therefore x y bar plus you have to add half to the y bar value, and z plus half is the C glide operation. So x and half plus z is the C glide operation. Y bar operation now gets added on a half. So therefore we have x y bar plus half and z plus half. The fourth equivalent point obviously gets generated because of the presence of the center of symmetry, which is shown up here. Once again we see that the translational periodicity will bring this into this position, the translation periodicity here. So 1.1 and 0.3 are already located here. The twofold the 2-1 screw operation has gone outside of the unit cell. We add one translation, so it comes inside, and there is a development of the 1/4 C glide. Along with that there is a development of the 3/4 C glide. So the C glide at 1/4 and 3/4 will invoke the formation of 4 equivalent points inside P21 upon C. So anything further about P21 upon C we will see in a few minutes. What we will notice here in this case of P21 upon C is that if you have a object which is located at this particular point, you have the unit cell that is available to that particular object. Let us say it is a molecule. Now you see that there is a half translation to generate 0.3, and there is also a half translation to generate this point, because you are adding 1/4 along the direction perpendicular to this, and therefore the molecules are, as I mentioned, well spread out inside this unit cell. Of course the unit cell dimensions now will adjust themselves so that the flexibility associated with the molecule can also be fitted in. If you look at the literature and if you analyze the Cambridge structure database and look at how many P21 upon C structures are there, in a recent evaluation it is found that something like 38% of the total, more than that in fact, 38 to 42% I think, of the all organic compounds solved so far go into this space group. The reason being that many of the organic compounds have an asymmetric carbon. The asymmetric carbon involved components will always go into a space group P212121. So, that is why I mentioned the space group now itself. When I say P21, 21, 21, what is the take home lesson? The take home lesson is that now we have 3 intersecting two-fold axes, one along x, one along y, one along z. That means that it has to be 3 directions which are at 90 degrees with respect to each other. Alpha, beta, gamma are 90 degrees with respect to each other. Obviously, there is no restriction and you have a two-fold axis on any axis, and therefore, A is not equal to B, not equal to C. So, A not equal to B, not equal to C, alpha, beta, gamma 90 degrees will define an orthorhombic system, and therefore, the space group P21, 21, 21 is in the orthorhombic system. And because of the fact that it is in the orthorhombic system, we will have 3 2-1 intersecting axes. Now, the question comes up, if we use the same logic as we have used in case of P21 by C, where we have shifted the axis by 1/4 and 1/4 axis as well as the plane. If there are 3 intersecting axes, what do we do? Because the Euler's theorem tells us that if there are 2 points which are intersecting at a point, the third symmetry operation will automatically get generated, but that third symmetry operation with respect to the point group will have to become a two-fold. So, if you have a, let us say 2 2-1 axes intersecting, we will discuss that when we actually derive the equivalent points of 2 1 2 1 2 1 at a later date. But what really happens is, if you have a 2-1 screw axis and another 2-1 screw axis intersects with that, based on Euler theorem, the third invariably has to be a two-fold axis. So, in which case we will have a space group P 2-1 2-1 2 and not 2-1 2-1 2-1. Then how can we generate this space group 2-1 2-1 2-1, which forms the another 38% of the total number of organic molecules in literature, which have an asymmetric carbon. They go into 2-1 2-1 2-1 preferably. So, how does the third 2-1 come in violation of the Euler's theorem? It is not violating the Euler's theorem. The Euler's theorem has to be modified. In fact, there is a corollary on Euler's theorem which tells that if there are such situations where the 2 intersections are generating a translation phi component, if there is a translation component involved, then we will have to separate them from each other. So, the origin now has to be arbitrarily fixed, but it has to be fixed in such a way that effectively the 3 axes intersect to generate a 2-2-2 symmetry from the point group point of view. So, the translational periodicity that is involved in crystals is something which we will invoke in order to have 2-1 2-1 2-1. That means only in crystals you can have the space group P 2-1 2-1 2-1. But what is very beautiful is that the organic molecules prefer to go in the space group 2-1 2-1 2-1. Organic components go into the space group P21 by C otherwise, and P21 by C again, as we have seen here, is a fairly straightforward set of equivalent points here. In this case, of course, it is only one single axis, and so there is no question of invoking the Euler's theorem, because the full symbol of this space group is P1 2-1 by C 1. So, that way we have a situation where we have the 3 systems P2 by M, P2 by C and P21 by C having translational involved components. How many translation involved components come up is discussed here. So, in a nutshell, what we will see now is that we have discussed the primitive lattices associated with the 2 by M symmetry. We now have to worry about the presence of the C-centered lattices. So, if we now think of a C-centered lattice, we should have a space group C21 upon M. We should have a space group C21 upon C, and we should have a space group C21 upon C, and also C2 by upon C. We have already seen in the earlier class that C2 and C21 are one and the same. It is just a question of shifting the origin by 1/4, and therefore, we will not have all those systems which I mentioned, as we will see in the next few slides, that the systems which we can have are limited. So, wherever there is a C operation coming up, once it is a C centered lattice, the 2-1 disappears and we will have only C2, and therefore, we have C2 by C and then C2 by m. We will not have C2 1 upon m, and that is something which we will have to discuss as we go further. So far what we have done is to see the way in which the space groups formulate, starting from the triclinic system to the monoclinic system. And in the monoclinic system we have examined the occurrences of non-translation involved components, the screw axis as well as the glide planes. Screw axis and the glide planes come only in the monoclinic system and definitely not in the triclinic system, because triclinic system has no axis of rotation. That is something we should remember. And so the triclinic systems have only 2 space groups, whereas there are several space groups which develop in the case of the monoclinic system. Further, we have also seen that the presence of the translation involved components will involve translations of the individual components depending upon the nature of the non-translational involvement participation in the space group.